They call it switch reluctance machine. You know, basically the reluctance of the machine is going to change. See, if this one is here, you can see how much reluctance you have. When this one moves here, we have a bigger air gap, right? We are going to have a bigger reluctance, right? Switch reluctance machine, permanent magnet machine, won't rotor machine, they are all synchronous machines. But we're not going to talk about the permanent magnet and switch reluctance machine. You know, in this book, we can find a little bit more material about it, but we're not going to talk about it. Permanent magnet machines, they're very, very popular these days. Very, very popular. All electric cars. Not just Tesla, you know, the only one I can say Tesla right now is still an induction machine. But the rest, electric and hybrid cars, all they're using permanent magnet machine. The reason the permanent magnets, they are very good, because instead of putting these windings, right, if you have a magnet, strong magnets, right, so you want to create a good magnet here, right? If we have a big magnet, a very good magnet, natural, so you don't have to put a winding here, this structure here is going to make the machine very small. And it is a very strong magnet. Remember, we were talking about the torque and force and those kinds of things. And the torque and force is there because of reaction of two fields, right? The bigger magnets, the better, right? So if you have a very good magnet materials, right? So basically, you don't need to put lots of winding here. Put very strong magnets here, because the machine is very, very small. And you know, for the mobile application, volume and weight is very important, right? So that's the main reason everybody is using the permanent magnets. They have very, very high torque, and the size is pretty small. But the problem with that is getting more and more expensive, you know. And there are people that are trying to find another way to go around magnets if they can. We're not going to talk about permanent magnet or switch reluctance machine. We're going to start with this cylindrical machine. Synchronous machine. The first thing we start with this one is the speed of the machine. If the machine has a P pole, right, and the frequency, I'm not talking about the motor, but it's going to be the same for the generator. And if the motor has a P number of poles, and the frequency of the voltage connected to the machine is F, so the synchronous speed, machine is going to rotate with the synchronous speed, we call it NF, and it's going to be 120 F over P. This is the frequency of the supply, and P is the number of poles of the machine. And the machine is going to start, and this is the RPM. This is the RPM. And this is the mechanical speed. You know the relation between the mechanical and electrical speed, right? We say electrical is P over 2 times mechanical speed, right? Exactly the same thing we said for the DC machines and induction machines. Now, let's look at the structure of the synchronous machine. Do you guys have a homework over the homework I gave you? So I want to show you which problem, you know. The homework, I think number 2. If you have by any chance, we have homework number 2. And I went over one of the problems here on the board. It was there was an IF, there was an A winding and B winding. I'm not sure those ones they were in the class. That one was a synchronous machine. Let me see here. I'm not sure if they give you here or not. Yes. Look at here. Problem number 4 of your homework number 2 is a synchronous machine, but it's single phase. So there is only one winding on the stapler. I think I solved one here on the board. We had 2 windings on the on the stator. I went over that one. Now, most of synchronous machines, they're three-phase. So let's see how the structure is going to look like. Basically, we have a rotor and we have a stator. Right? We have a rotor and we have a stator. We have a three windings for the stator. So if you remember, I talked about it. I said the windings usually they are sinusoidal, right? You know, we put less here, more maximum here, and let the gain will go down to 0, right? They call it sinusoidal distribution, which all the motors they are like that. All the motors and generators they are like that because you want to have a sinusoidal output voltage and current. Here when I'm drawing it, I'm going to go with the central winding. I'm going to put only one slot. I'm going to consider one slot. In the real machine, it's not like that, but in the theory, it's not going to be different. So basically, this is my phase A, right? I have a three-phase winding on my stator. This is a three-phase machine. I have a three-phase winding here. Basically, I have one coil going like this, right? This is the phase A. So let's call this one, for example, this one current going inside. Let's call this one A, and this one is going to come out, right? Let's call the other side A prime, right? We have one here. So B is going to be 120 degrees far from this one, and C is going to be another 120 degrees far from this one. So basically, if you draw those ones, B is going to come here. Look at here. This is the direction here. So phase B is going to be here, and phase C is going to be here. Right. Let's put the winding in. So basically, this is a D dot D prime. This one is going to be C and C prime. So I have a three windings in my stator. As I said, I call this one central winding. Why? Because only I consider one slot. I put all my winding in these two slots, right? But in reality, phase A is not going to be only one slot. It's going to start from here, go all over here, right? For example, 1, 2, 3, 4, 5, 6, 10. Let's say phase A has, I don't know, 100 turns, right? You start from here, 0 here, 2 turns here, 5 turns here, 10 turns here, 20 turns here, and the same thing over there. Basically, we put the 100 turns here, all over here, but with a sinusoidal distribution, right? That one is for the real machine, when you design the machine. I'm not going to go to that part. So basically, I have a three-phase machine, phase A here, phase here. Now, what's the magnetic axis for this phase? Magnetic axis, if you look at it, see this current is going to go here, come here, going here, right? So basically, if you look at the flux is going to be like this. Let me see here. It's going to be like this. So the current is coming like this, right? You put the thumb in the direction of the current. This one is going to show you what? The magnetic flux for phase A, right? So we call this one A axis or FA axis. Let's call it FA, the magnetic flux of the phase A, or phi A axis. I don't know, phi A. Let's call it phi A. Right? This is the flux of phase A. If you want to find phase B, it's going to be the same direction here. Phase B is going to be, let me see here, going there. Basically, it's going to be this way. This is a phase A. Phase B. This is a phi B axis. And this one is going to be phi, it should be 120. Maybe this is not very good enough. This one should be 120. And this one should, I don't want to write it, this one. And C is going to be here. I'm not going to put C here because it's going to get parallel. I don't want to put that one. We have phase A, phase B, and phase C, right? We have three magnetic axes for each one. Now, let's put the rotor axis here. Sorry, rotor winding. The one I put it over there, look at here. I erased. You know, the one was with the solid pole, right? I put the winding there. This is a cylindrical. Let's say put another slot here, right? And one here. So now I'm going to put another winding here, right? So this one will be not here and not here. I'll call this one F and F prime. F stands for the field, you know. So we put this field winding on the rotor. So let's see how is going to be the magnetic axis for this one. The current is coming here, going here, going here. You put your finger here, so I put your finger down. So the current is going this way. I want to go this way. Now I want the axis to be down. Oh no, yeah, that's right. That's right. This is correct. So this one is going to be perpendicular to this one. This is going to be phi f axis, right? Phi f axis. So let's call this axis theta. Let's call this angle theta. There is a reason I'm putting it at. Why? Because this machine is rotating, right? This machine is rotating. Basically, this field is rotating like this, right? When I rotate this one this way, so this one is going to go like this, right? This angle is going to change. It's going to become more and less, right? But if you look at between the A and B, always, how much is the angle between these two? 120, right? They are not moving. They are stationary. Between A and C, 120. Between B and C, 120. I'm going to use these numbers, you know. Keep in mind, you know, I'm going to use them. I'm measuring this one 120 and that one is changing. So I have 3 windings here. And I have one here. This one is rotating. Now I want to talk about the inductances of this machine. And let's call this one, let's say this one is rotating with the speed of omega. Let's say the rotor is moving with omega, or omega m. I'm going to just call it omega m or omega. So basically this theta is going to be omega t plus delta 0. Delta 0 is the initial angle. Let's say this motor is not plugged in to the wall, right? So this one is standing somewhere, I don't know where, right? There is some initial angle, right? We call that one delta 0, right? Now when I plug it to the wall, it starts to rotate, right? So basically, let's say initially was here, we call this angle delta 0. Now this one is going to move. How much is the theta? The initial angle plus omega t, right? So, now I want to write a lambda A. How much is the lambda A? Lambda is a flux linkage of phase A. I have a 4 winding system here. Let's go back to the exam you had. You had a 2 winding system, right? Then we had a 2, we say lambda 1 is L11 I1 plus L12 I2, right? If I have 4 winding, L11 I1 plus L12 I2 plus L13 I3 plus L1, all of them, 1, 2, 1, 3, 1, 4, right? Times the current. How many winding I have here? 4. So basically I should put 4 terms here. So it's going to be LAA. When I put it like this, means it could be variable. It could change with the time. I'm going to calculate those on how much they are. But it could be variable when I write it like this. If I write it like this, means it's constant. It's not changing. It's a constant value. You know, just to know this is the notation I'm using. When I put it that way, the script means it can be a variable number. It can change with the rotation of the machine. But if I put it like the one over there on the left, means it doesn't matter. Always is a constant number. Let's start with this one. It's going to be LAA. You tell me. What? IA. Okay. LAB. ID. LB. LAC. IC. LAF. IF. Right? That's what the why I'm calculating the lambda A? Before going there, I started to calculate it, and I say why I'm calculating that. Why? I want to calculate the voltage across the machine, right? In the back, inside the machine. What's the voltage? Voltage of phase A inside the machine, right? Whenever we have a motor or generator, we have a terminal voltage which we connected to that, right? And we have back EMF inside the machine, right? What's that back EMF? That's a voltage, right? It's a d lambda over dt, right? D lambda over dt is a voltage. So basically, I'm going to write all the flux, equation, and simplify it as much as I can. And after that, if I take a derivative of that, it's going to give me the back EMF for the machine. And when I simplify that one, at the end, I can draw the equivalent circuit of the machine, right? So how about lambda b? I'm going to write it quick. It's going to be, I'm going to put it LA. It's going to be LBA. But because these systems are linear, LAB and BA, they are equal. LBC, LCA, they are CB, they are equal. All of them they are equal. So I'm going to use only LAB. LAB, IA, BA, LBB, IB, plus LBC, IC, plus LBF, IF. So lambda C is going to be LCA, IA, plus LCB, IB, plus LCC, IC, plus LCF, IF. Lambda F is going to be LAF, IF, IA, plus LBF. Actually, I should FA. I should say FA. Right. We have 4 winding. I wrote the equation for this. This is good. Now I'm talking about this one. Let's go back to the exam. I think a few they did this. He said the windings they are parallel, right? When windings they are parallel, what does it mean? Because lots of people they put the current the same for the windings. Same voltage, right? When the voltages are the same, what does it mean? Lambda is the same, right? Because the voltage is d lambda over dt, right? So basically, simply you could have put the lambda 1 equal to lambda 2, find out how much is the relation between I1 and I2. They did some, they did. I'm not saying that, but some they did. But most of you didn't do that. You can find out what's the relation between I1 and I2 and replace it and calculate. Now we have all these fluxes here. Let's go and start to calculate these values first. First of all, let's put it here. LAB is equal to LBC, LBA, and I'm going to explain it to know why. Equal to LBC, LCB, equal to LAC, and LC. I was going to write this one, write this one only. But at the end, they're going to be equal. If you don't want to put it right now, put it right. But they're going to be equal. I'm going to say why. They are all the same. Now, let's start with the LA. Going back to the first parts of the course, we said if we have an inductor like this, I don't know, we have a gap here, for example. This is the N. I don't know. How much was the L here? N over R, right? The reluctance of this circuit, right? N is number. It is a fixed number, right? And if R also is fixed, L is going to be a fixed number, right? But for example, let's say if you have something like this. If you have something like this. And somebody can pull this one, right? Now R is different. R is variable, right? Because if this one goes here, the air gap area is going to change, right? So basically, this is a variable resistance, right? Variable reluctance, right? So basically, L is not constant. L still is N squared over R, but because R is based on where we are, right? based on where we are going to locate. So R is a different